So here we have the Brayton refrigeration cycle, and we have been provided that the air enters the compressor at this conditions, at this pressure and temperature, with a volume flow rate of 1.4 meter cube per second. Okay, so we know the conditions at state one. And we also have been provided with a pressure ratio. So P2 by P1 is given as 3. And the turbine inlet temperature is given. So T3 is given. And the compressor and turbine, the process is not isentropic, but they have an isentropic efficiency of 80%. Using this information, we need to calculate the net power input, the refrigeration capacity, and the COP. Okay, so well, this is sort of the usual stuff that you calculate for any sort of refrigeration systems. So the first step is certainly to get the enthalpies at all states. So let's start with the information that's given to us. This is all what we have been provided. Okay, and we know that P2 is equal to P3 because it's a constant pressure heat rejection process, and P1 is equal to P4 because it's a constant pressure heat addition process. And we have both P1 and P2 given to us. So let's start with state one. Okay, we have the temperatures. Again, we're going to treat air as an ideal gas with variable specific heats simply because nothing is mentioned about constant specific heats. So from the ideal gas table, you get the value of enthalpy at state one, H1. And since we have the pressure ratio, we'll find out the PR1 from there at state one. Now, the process 1 to 2S, right, is an isentropic process. So the pressure at P2S is equal to P2. So we're going to make use of this and calculate PR2 from here. Okay, PR2 by PR1 is exactly equal to P2 by P1 for an isentropic process. So using this value here, right, which we obtained simply by making use of the pressure ratio, which was given 3, and the PR1, which we obtained from T1, we obtain now PR2, and using this PR2, we just have to go to the table, and what we get is H2S. Okay, this would be the enthalpy if the process is isentropic, but we know that the process is not isentropic. So what we need to do is we need to get H2, right? So we can get H2 value from the isentropic efficiency. So the isentropic efficiency of the compressor is given. It's equal to the actual work input, sorry, isentropic work input divided by the actual work input. Okay, and this is value is given as 0.8. So H1 is known, H2S is known. If you want, you can go ahead and determine H2 from here. But for us, since we want to determine the net power input, we can for now just determine the compressor work input per unit mass. Okay, the compressor work input per unit mass would be H2 minus H1, and from this formula, it simply be equal to H2S minus H1 divided by the isentropic efficiency. Okay, we know H2S, we know H1, we also know the isentropic efficiency. So plug in the numbers, and you get this value for the compressor work input per unit mass. Now, this is the simple part, but remember here, we can't neglect the turbine work output per unit mass. So we also need to get that. Again, the process is very straightforward and simple and very similar to what we just did. So we again have the temperature at state 3. So using that, we get the enthalpies and PR3. And we consider the isentropic process 3 to 4S. Okay. And using this ratios of relative pressures to the actual pressures, which works out for only isentropic processes, we're able to determine PR4. And with PR4, we can determine H4S by interpolation. So remember, this is not what is at the exit of the turbine. We need to get H4 here, right? Because we also need to calculate the refrigeration capacity. So we calculate that by making use of the isentropic efficiency of the turbine. Okay. So here we know H3, we know H4S, we know the isentropic efficiency. When you plug in the numbers, H4 comes out to be 235.24, higher than H4S certainly. Okay, so now we have all the enthalpies that we care about. We need to go ahead and now determine the stuff that we need. So first of all, for net power output input, we need to provide we need to calculate the net power input in kilowatt. Do we have all the information that we need, or do we need something else? The net power input has to be provided in kilowatt, not in kilojoule per kilogram. So do we need any information?
The mass, yes.
Exactly, we need the mass flow rate. Okay, so the turbine work output per unit mass can be simply calculated as H3 minus H4, and this is the value once you have calculated H3 and once you have calculated H4 as well. Now we also need the mass flow rate. We have been provided the volume flow rate at state 1. So we make use of that and either divided by V1 or multiply by density. It's the same thing, right? It's the same formula that comes up. You plug in the numbers and this is what comes out to be. We have calculated the mass flow rate many times, so you exactly know what to do here. Okay, so this is the mass flow rate that we have, and we already know the compressor work input per unit mass, the turbine work output per unit mass. So we just need to multiply the mass flow rate with these quantities. Okay, so mass flow rate times these quantities, which are kilojoule per kilogram, gives us the net power input. So the net power input is about 108 kilowatt, 108.5 kilowatt, let's say. So that's the first part done. Now for the refrigeration capacity, well, it's simply mass flow rate times H1 minus H4. Okay, that's the reason we wanted to determine H4 as well. So we have H1, we calculated H4. The mass flow rate also something we calculated it here. So this comes out to be 63 kilowatt. So these are relatively large numbers, right? This is a reasonably large cooling capacity. Now the COP, it's simply the refrigeration capacity Qn divided by the net work input. All right. The difference here is that we are not only looking at the compressor work input, but we're looking at the net work input. So you cannot neglect the work done by the turbine. So when you divide it by when you plug in and divide these two numbers, we get a COP of about 0.58. Now, just to compare, this COP is lower than the beta values that we were obtaining for vapor compression refrigeration systems, which are typically greater than 1, right? So this is what we were saying all the way, right? When you use a Brayton cycle, the COPs are going to be lower for sure, but in some cases, it makes sense to go ahead with a Brayton refrigeration cycle because the vapor compression cycle is not suitable for that specific application. And as we discussed, the two applications are very low temperature applications where the vapor compression, where the refrigerants may get frozen below 100 minus 100 degrees Celsius, let's say, or for meeting the cooling needs of air conditioning system aircraft systems.